On May 29, 1919, two teams of astronomers positioned themselves on opposite sides of the planet with a single objective: photograph stars that, according to classical physics, should be invisible. The expedition would either validate a theory so radical it suggested space itself could bend, or it would invalidate 4 years of work by a German physicist named Albert Einstein. The human element here is Arthur Eddington, a 36-year-old British astronomer and Quaker pacifist who spent World War I defending Einstein's work while his colleagues dismissed it as enemy propaganda. Eddington placed his professional standing at risk on this expedition. If the photographs failed, his credibility within the Royal Society would collapse. The stakes extended beyond one career. The expedition would determine whether Newton's 200-year-old gravitational model was fundamentally incorrect. The theory in question was general relativity, published by Einstein in 1915. It proposed something that contradicted observable experience. Mass doesn't exert attractive force through empty space. Mass induces curvature in space-time geometry itself. A massive object warps the four-dimensional manifold of space-time. Light traveling through that curved geometry follows altered null geodesics. The light's path bends not from force, but from geometric distortion of the medium through which it propagates. This creates a testable prediction. If you observe a star positioned directly behind the Sun, its light should follow a curved path around the Sun's mass-energy distribution. From our perspective, the star's apparent position should be displaced from its actual coordinate position. The effect would be minimal. Einstein calculated a deflection of 1.75 arcseconds, roughly the angular width of a quarter coin viewed from 3.2 kilometers. But it was measurable, and it was precisely twice the deflection Newton's model predicted. There was one constraint. You cannot photograph stars near the Sun under standard observational conditions. The Sun's luminosity overwhelms their photon flux. You need the Sun's direct light blocked. You need a total solar eclipse. The next total solar eclipse visible from Earth would occur on May 29, 1919. The path of totality would cross the Atlantic. Eddington organized two expeditions. He would lead one team to the island of Principe off the west coast of Africa. A second team under astronomer Andrew Crommelin would travel to Sobral in northern Brazil. Both locations offered unobstructed views of the Hyades star cluster, which would be positioned near the Sun during totality. The Hyades contained bright stars, whose positions were already precisely mapped in multiple reference catalogs. Photograph them during the eclipse, compare their positions to reference photographs taken months earlier, and measure any positional displacement. The logistical requirements were complex. Eddington's team transported a complete astrophotography laboratory across the Atlantic by steamship, then by smaller watercraft to Principe. The equipment manifest included a coelostat, a mirror system that tracks solar motion and reflects light into a stationary telescope. The telescope itself was a 13-inch reflector. They packed glass photographic plates, each one irreplaceable. The entire operation depended on atmospheric conditions. Cloud cover during the 427-second period of totality would render the expedition inoperable. May 29th arrives. Principe is overcast. Cloud cover persists at altitude. Eddington's team waits. At 14:13 hours local time, the moon's umbral shadow begins its approach. Totality initiates at 14:13 and terminates at 14:20. As the moon's disk transits across the solar face, the cloud layer thins. Partial breaks appear in the overcast. Eddington initiates plate exposure. He captures 16 photographic images during the totality window. Solar corona becomes visible through gaps in the cloud cover. Star positions register on multiple plates despite intermittent obstruction. Then the Sun re-emerges from behind the lunar disk and the observation window closes. Eddington cannot develop the plates immediately. The chemical development process requires controlled laboratory conditions unavailable on Principe. But he examines two plates using a basic field measurement technique. The star positions show displacement from their catalogued coordinates. He records in his expedition journal, "The one good plate that I measured gave a result agreeing with Einstein." Meanwhile, in Sobral, Cromelin's team operates under clear atmospheric conditions. They deploy two instruments, a 4-inch lens and a larger astrographic lens borrowed from the Royal Observatory, Greenwich. Both capture high-resolution images of the Hyades star field. The Sobral team photographs the same stellar objects, then disassembles their equipment for the return voyage to England. The analytical work begins back in England. Eddington and his colleague Charles Davidson process the Principe plates. The procedure involves microdensitometry, measuring the precise pixel-level positions of star images on glass plates, then comparing those positions to reference photographs taken in July when the same stars were visible at night, with angular separation exceeding 90 degrees from the sun. Any measured positional shift indicates light deflection through curved spacetime. The Principe data shows marginal signal quality. Only two plates are usable for quantitative analysis. The measured deflection ranges from 1.61 to 1.98 arcseconds, within range of Einstein's prediction of 1.75, but with significant statistical error bars. Standard deviation exceeds 15%. The Sobral data presents different characteristics. The 4-inch lens produces 19 high-quality plates with sharp star images. The measured deflection averages 1.98 arcseconds, within 0.23 arcseconds of Einstein's prediction. The margin of error is 13%. The larger astrographic lens produces deflections of only 0.93 arcseconds, closer to Newton's prediction of 0.87 arcseconds. But post-analysis reveals the astrographic instrument suffered thermal expansion during the eclipse observation period. Solar radiation heated the mirror assembly. The substrate warped. The optical path length changed. The data from that instrument contains systematic instrumental error. Here is the logical friction. Two instruments observe the same physical phenomenon. One measures deflection consistent with Einstein. One measures deflection consistent with Newton. Both cannot be correct. The physical geometry of spacetime either curves under mass-energy stress or it does not. Eddington must make a judgment. Accept the data that supports the new theory and dismiss the data that supports the old theory, or vice versa. He chooses to trust the 4-inch lens data. He classifies the astrographic data as instrumentally compromised. Eddington presented the combined results to the Royal Society and Royal Astronomical Society on November 6, 1919. The conclusion was unambiguous. Light deflection matched Einstein's prediction. Newton's model was insufficient. General relativity was validated. The announcement generated international coverage. The Times of London published the story with the headline, "Revolution in Science, New Theory of the Universe, Newtonian Ideas Overthrown." Einstein became an immediate public figure. The expedition had not just confirmed a theory. It had demonstrated that physical reality operates according to principles that contradict sensory intuition. But here's the detail planted earlier that only now makes analytical sense. Eddington was a pacifist Quaker. He had defended Einstein's work during World War I, when anti-German sentiment dominated British academic institutions. Some historians argue Eddington's confirmation of general relativity was influenced by confirmation bias. He wanted Einstein to be correct. The Principe data was marginal with high error. The Sobral data from the astrographic lens contradicted Einstein. Yet Eddington dismissed that data as instrumentally flawed and embraced the 4-inch lens data that supported Einstein. Later expeditions confirmed gravitational lensing with far greater precision. Modern measurements using very long baseline interferometry and the Hubble Space Telescope show Einstein's prediction is accurate to within 0.01%. But in 1919, the margin of error was statistically significant. Eddington made a judgment call. He chose to trust one data set over another based on instrumental analysis. He was correct. But the question remains, did he confirm the theory because the data was conclusive, or because he believed Einstein's geometric framework was more internally consistent than Newton's force-based model? The phenomenon Eddington measured is now called gravitational lensing. It's not just a theoretical curiosity. Astronomers use it as an observational tool. When a massive galaxy cluster sits between Earth and a distant galaxy, the cluster's mass-energy distribution bends the light from the distant galaxy, magnifying it through gravitational amplification. This allows observation of galaxies too distant and too low in apparent magnitude to detect directly. In 2019, the Event Horizon Telescope used gravitational lensing effects to capture the first image of a black hole's photon sphere. The black hole's mass warps spacetime so severely that light follows closed orbital paths around the event horizon, creating a visible ring structure. That image exists because Einstein was correct. Space bends. But the 1919 Eclipse expedition wasn't just about proving a theory. It was about something deeper. It demonstrated that the universe doesn't conform to human sensory experience. Gravity isn't a force acting through empty space. It's geometry. Time isn't a universal constant. It's relative to the observer's reference frame. And light, which we perceive as traveling in straight lines, follows the geodesics of curved spacetime like a particle constrained to a surface. Arthur Eddington died in 1944. His obituary in the Royal Society's Journal noted his role in confirming general relativity, but focused more on his later work in stellar astrophysics and stellar nucleosynthesis. The 1919 expedition became a historical footnote in his career, yet it remains one of the most consequential observational measurements in physics. The question left unanswered isn't whether gravitational lensing is real. We know it is. The question is whether Eddington's judgment in 1919 was scientifically rigorous or influenced by theoretical preference. The data he dismissed contradicted Einstein. The data he accepted supported Einstein. He made the correct call, but did he make it for the correct reasons? That ambiguity is what makes the 1919 Eclipse expedition more than a physics experiment. It's a case study in how science actually functions, not as a purely objective process, but as a human one, where judgment, interpretation, and theoretical commitment intersect with observational data. The stars bent. The theory held, but the man who confirmed it was not an algorithm. He was a Quaker astronomer who believed in geometric elegance, who defended an enemy scientist during wartime, and who placed his professional credibility on 427 seconds of totality on an island off the coast of Africa.